Oh, you didn't start yet?
Hello and welcome back to Calculus1 section. I have to check, guys, come on. Section 3.2, where we're going to talk about derivative as a function. Last class, I hope, I can check, but I don't want to. We had a problem, I guess, where we said that f of x is, let's say, x squared, and then we went through calculation to find the derivative using that limit procedure of the difference quotient. So I'm going to repeat that procedure now, just as a quick review, and we are going to see that this particular function, x squared, changes into what we are going to calculate 2x. So our quadratic function changes into a linear function. And that answer we called last time the derivative, and we said that that one generates the slopes of all of the tangent lines along x squared. So any point you pick, you will be able to find exactly what the tangent line is, because the derivative would be computing the slope, and then you have to just compute the y-intercept. So if you recall the formula, let's write it here. Now again, this formula is in chapter 3, but the calculation is chapter 2 limits. So this calculation is definitely on your exam, and we can call it either limit of different quotient, or we can call it the derivative. It's the same thing. So we have the limit, h goes to 0, of f of x plus h minus f of x divided by h. So this was the formula. I'll put it on a cloud. And you have this little prime over here, and that little tick mark there denotes the first derivative of the function. So now, when I compare the formula and what I have over there, I see that I need to create f of x plus h first, and that is going to be x plus h everything squared, which when you FOIL, there we go, FOIL, it's going to be x squared plus 2xh plus h squared. So now, the derivative f prime is equal to, we have our limit, h goes to 0, of x squared plus 2xh plus h squared minus f of x, which is just x squared, divided by h. So now these two cancel, and you see that you can factor out h. You get 2x plus h divided by h. Cancel these two, and we get that f prime of x is equal to, when you send h to 0, you just get 2x. This 2x, it's a function, right? And our title today is derivative as a function. We want to compare this function and the original function and see which way these two are connected in some sense, and what we can read off of the function and so on. There was 10,000 people clapping, by the way. So now, so let's go and take a look at this situation. What I'm going to do is graph both of these functions on the same coordinate plane, and we're going to take a look at the features of one and the other and see how they're connected. So here's our x squared, that's a parabola. And here's our 2x squared, which is the derivative. So I'm going to label f prime of x, which is the red line, and f of x, which is the black line. So we have those two. One very important, so we're going to actually just cover, I think, 2 out of 3 things that we need to know in the whole section, right here in this picture. So one of those extremely important ideas is to see over here that when f prime of x cuts through, so when f prime of x cuts through x-axis, f of x has min or a max. Okay? So when f prime cuts through, you see that the red line cuts through this thing, and you have the minimum. All right? He won the raffle. Watch him drive off. Bye. All right, so one of the features is this. The next feature involves looking at, again, f prime and f of x at the same time, realizing, let's go on the right-hand side. I'm going to poke the arrow both ways this way and say when f prime of x is less than 0, meaning below x-axis, f of x is decreasing. Do we all see that the black line, f of x, is decreasing on the same interval where the red line is below x-axis? We all see that, right? Which is to the left of the y-axis. So in this region here, I'm going to erase this. In this region here, when I remove it, what you are going to see is the black line is decreasing, the red line is below x-axis. So if the derivative is negative, the f of x is decreasing. Finally, on the other side, I'm going to also poke the arrows and clearly, right, use a similar statement like the orange one. If the derivative is positive above x-axis, the function is increasing. So when f prime of x is larger than 0, so above x-axis, f of x is increasing. So this one picture clears out 3 out of 4 things that we need to know, which is awesome. So now I'm going to come up with a completely new problem. And take a look at what we might have as a derivative. You are able to sketch the graph of the derivative function looking at the graph of the function without doing any calculations, which is really cool. So let's say you have, again, I'm going to color code this lecture completely the same way. All of the f of x functions will always be black, and all of the f prime derivatives will always be red. So you will always, from problem to problem, you will always be able to tell which one is which. So now I'm going to draw this. So, in blood over here, I'm going to remind you of a statement which I made numerous times so far, which says derivative measures the change. Derivative measures the change. The change can be positive or negative. You can be gaining money, you can be losing money. You can be gaining weight, you can be losing weight. Right? It's a change either way. The overall weight of your car is constantly changing as you drive. Why? Gas. Gas is getting converted into energy to move the vehicle. Therefore, the weight of the gas that remains in the gas tank is always the same. It always changes down where your weight remains the same. Even if you're eating in the car, your weight is still, the system doesn't gain weight because you are eating, because the car already had the food and you, right, inside. So that's already, whether the food is inside you or on a seat next to you, it doesn't matter, right? That system is always going to have the same weight. The gas is depleting. So the system is losing weight as you are driving around. So
what if you litter and throw the garbage out?
It's $200 if you get caught. Okay. They have signs posted on the side. I'm not sure if you noticed. So that's what happens if you litter. Was that a question?
No.
All right, good. I'm glad that I could see all the time. All right, great. Now, what I am going to start doing here first is establishing the maximum and minimum values, because we learned in the previous example that anytime you have a minimum or a maximum value of the function, derivative is going to cut through x-axis. So I'm going to have my red points on the same x value, and my derivative is going to cut through the x-axis wherever the black line, which is a function, wherever the black line has min or a max. Now, we learned that if the function is increasing, which is this part over here, if the function is increasing, the derivative must be positive, must be above x-axis. So we're going to have something like that for the first part. Because the function was increasing, derivative must be positive. We can say, for this piece over here, f prime is bigger than 0 because f is inc, increasing. So that's for that piece. Now look what's happening for the second one, right? You have a decreasing piece. Over here, your f is decreasing. Well, if f is decreasing between these two values, right, then I don't know if I'm going to say it's common sense or it's not common sense, but we know that the derivative is going to be negative. So we have this. F prime is less than 0 because f is decreasing. Then we have this because f is increasing. If f is increasing, so f is increasing and the f prime is bigger than 0. So it's very easy to spot, looking at the derivative, And finally, the black line, which is the derivative, is decreasing, and the derivative will be negative. So f prime less than 0 because f is decreasing. And now, for the moment, I am going to delete the black line and then, by the magic of the undo button, bring it back from the dead. Yeah, as you can see, it's nothing special. And the reason for it is, if I want to use this graph, where I can say that, let's say the black line represents the stock price, money on the y-axis, and a time on the x-axis, right? You know what they look like, right? A heart attack thing going across. And that would be the black line. So you are looking at the black line, and as you're looking at the black line, you're saying, I'm making money, making money, making money until you get to that first maximum. And then you are losing money, losing money, losing money. You hit the minimum. Then you are making money, again to the maximum, and losing money, and so on. But look what I can do. If I kill the function, which I'm eventually going to bring back, if I kill the function, I don't have a function anymore. I'm just looking at the derivative. All I need to see here is at which points, right, for which values, the derivative is below x-axis or above. So I don't have to worry about function going up or function going down or anything like that. All I'm going to say is cut on the x-axis for all of the intervals where the red line is above x-axis, I'm making money. For all of the intervals where the line is below x-axis, I'm losing money. That's much faster to look at and make split-second decisions than actually looking at the graph. The graph of the derivative is much faster to tell us growth or decay, right, the change that is happening, than if you look at the original problem. Want to see the magic trick? All right? Wow. Usually, magicians make things disappear. I'm telling you, this class is the best thing you ever had. Next problem. We're going to take a look at driving, let's say. Velocity with the distance covered. Whatever. So you go into the car. The car is parked at the parking lot with a zero velocity. I hope you start that way, right? Otherwise the car is drifting and you're jumping in, right? So you did the whole routine, right? Every time you are supposed to drive, you walk around the car, look at the car from all angles, then you get in, strap, right? Those things. And you start driving eventually. So now you're going to drive like that, increasing velocity to certain value, and then you are driving, actually not for some distance, you're driving some distance at the constant velocity. Let's say it's 40 miles per hour. You're on one of the county roads, let's say. 40 miles per hour. Then you have to brake because there is a farm Did you say lion? I said county road. I'm not safari. So pay attention. So now you are stuck behind a tractor or something, right? Your farm equipment. Now you're doing 20. Now in reality you do that forever here, but let's say you know a little bit. Now the speed limit is still 40, but you have to make up.
How much you making up there?
Don't worry about it. And then you drive straight, and then you get pulled over. So, yeah, not every story has a happy ending, okay? Disney lied to you. Yeah. Yeah, exactly. There is always that happily ever after. It's just that it doesn't work. Anyway, so this is the graph of your velocity and within the distance you covered. You can also change it into time. I don't care. What I'm interested in is the derivative, because I want to see the change in velocity. So now, on the same graph, I'm going to take a look. So this black line is the f, right, the function. And I want to look at the f prime, which is the derivative. So what is happening now with the... Actually, you know what? I'm going to change this distance into time for a reason. So let's go, change this to time. And you can say you were accelerating. Wow, 2 minutes, really? All right. It's terrible. You're accelerating for 2 seconds. No, this was actually 2-second acceleration to 40 with a regular car. Like Tesla gets it to 60 in 2 seconds, right? So maybe you can pull it off, whatever. How about A, B, C, D? E, F, G. No need to sing, just put the values there. All right. So what is happening in the first one? You are accelerating. Your velocity is going up because you push the gas pedal. The change is a positive change. You can calculate the value. So you are going to have the acceleration, and you can calculate the slope of this, as you can see, is 2 over 1. 2 over 1, right? So the value over here is the slope of 2. So if we're going to call for the red, we're going to call this, let's say, 2. You are going to have a flat piece right there because you had a constant acceleration. The slope is always a value of 2. Now, what is the derivative for the flat piece as you are driving? Derivative is 0. Why? There is no change. Very good. Here it is. I'm going to unveil the sentence that solves this. Derivative measures change. Well, for this flat piece over here, there is no change. You're always driving 40. So the derivative is going to be 0, and it's going to be on the x-axis. Then, remember, we got behind a tractor of some kind, or some farm equipment, whatever it is, right? Is driving 20 miles per hour. So we have to go behind it and drive slow until we can pass it. So now you're looking at that, and you had to brake. So now you are braking, and you have a negative 2 value over here because you go 2 units down, 1 unit over. So that's a negative 2 value. And that's that red piece between B and C. It's a red piece. Then you are hitting the again, flat. This is the time as you are driving behind this tractor or whatever it is. Your derivative is 0 between C and D again, because there is no change in your speed. Remember, derivative measures the change. If there is no change, the value of the derivative is 0. And at D, time D, whatever is in front of you is off the road, and you can accelerate. This acceleration is going to be, looks like 2 again, because 2 over 1, 2 over 1, whatever. So between D and E, we're going to have another acceleration, positive. Then we are going to drive, unfortunately, over the speed limit. And then, as we are getting pulled over, right? What do we got over here? 1, 2, 3, 4, 5, 6, 7. Slope is negative 7 over 1. So 1, 2, 3, 4, 5, 6, 7. Negative 7. So negative 7 is here. And that's the one to stop. So now if you take a look at the derivative, it's a step function, right? It's a piecewise function of all of these little flat slopes, because the only functions we used were linear functions. If you have constant piece, there is no change in a constant, meaning that derivative of a constant is 0. Derivative measures change. There is no change in a constant, therefore derivative of a constant is 0. So now we learned that let's point with the blue. Derivative of a constant is 0. Derivative of a constant is 0. So that's what we learned from this picture. We have one more concept to learn, and we're done. So the last concept we are learning is that the location of the vertical asymptote between f of x and f prime of x is preserved. So the last part, let's go orange. Location x equals a of the vertical asymptote in f of x and f prime of x is the same. Well, you can phrase this any way you want, I don't care. We are going to use our favorite example for calculus, 1 over x. If you remember that your derivative, we did it in class. F prime was negative 1 over x squared. So if I draw for the 50th time so far, 1 over x function, if I remember that 1 over x squared looks like this, but then I have a negative which would flip it. Flip because of the negative sign. So the black function is f of x. The red function here is 1 over x squared, which is f prime. Negative 1 over x squared, sorry. And f of x equals 1 over x. The concept that we are learning right now is that both of these functions, x squared and 1 over x, 1 over x and 1 over x squared, both of them have the vertical asymptote at x equals 0. So both functions have va at x equals 0, which is why I said that the location is the same. So does this make sense? Well, yeah. You have your function decreasing. The black line is decreasing, so the red line has to be below x-axis. And then for the second part of the graph over here, it's still decreasing. So the second part also has to be underneath the axis. And neither of the two functions are defined at 0. So when you do the derivative, your vertical asymptote is going to stay at the same spot. And taking the derivative of 1 over x gives us negative 1 over x squared. They have the asymptote at the same spot, x equals 0. And we see that all of our f decreasing and f prime less than 0 and f prime less than 0 because f was decreasing. So let's recap, and that's it. I hope you're not disappointed. So when you go back to the introductory example with the x squared and 2x, we know that the 2x is the derivative of x squared. So 2x is the derivative of x squared. I graphed both of those functions on the same coordinates system over there. And we introduced the first three concepts. One says if the function is decreasing, derivative is negative, which means below x-axis. When the function is increasing, the derivative is positive. And whenever function has min or a max, it has a 0. Now we strengthen that idea with this example. You see 3 extreme points, you see 2 maximum values, 1 minimum value, and every single time you had a min or a max, your derivative hit the x-axis. So those are the 3 red dots. Now, we use the same idea. The first segment of the line to the left of the maximum was increasing. The black line, which is the function, was increasing. Therefore, the derivative has to be above x-axis, and we know it has to hit that minimum point. It has to hit the point on the x-axis because that's where the maximum point was for the function. And you just follow around. Anytime the function is anytime the function is increasing, you have the positive derivative. Anytime function is decreasing, you have negative derivative. With this example, we learned that anytime when you have the constant, right, part of the function, that means that the derivative is 0. There is no change. Derivatives measure change. Since the constant has no change in it, derivative is change, which is why we have those 3 parts of a function which are sitting on the x-axis. There is no change there. You are not accelerating, you are not decelerating, you are driving at a constant speed. So the change in speed is 0. The way to change the speed is to either accelerate or decelerate. Both of the pedals that you are using in a car are acceleration pedals. One is making your speed change up, and the other one is making your speed change down. In case you have a car with 3 pedals, upgrade. It's 21st century. Holy nightmare.
Why, would you like a standard? You don't like a standard?
I don't even have to think about it. It's out of picture. Why would you bother? It like the shifter just wears out the skin on your right. Then you have to put the glove. You put the glove. It just gets the moist and damp inside, and then just mold, and then you lose your hand. It's like no. Well, I like extremes. What I can say. The last concept we learn is the concept of the vertical asymptote. So between the function, if the function had the vertical asymptote at the particular location, the derivative will have the vertical asymptote at the exactly same spot. So vertical asymptote location is preserved, and that is all for this. The derivative is a function, and last class we said that the derivative generates the slopes of tangent lines that you can draw along. So we'll have obviously more to say about that as we go through the chapter. Right now we just need the skill, the ability to draw the function if you have derivative given, or draw the derivative if you have the function given, and your MyMathLab will be littered with these problems, so you guys can enjoy that. If you have any questions, we'll deal with that on Thursday.